Welcome to Lab 5, Faraday's Law. This is a pretty long lab, so I'm going to be going a little quickly. Introduction. So, the goals of this lab and the purpose is to collect data on a magnet falling through a tube of aluminum foil and create a computational model for the interaction and compare the time that it takes for that magnet to fall through the tube in our experiment and the computational model. And so a brief preview of the results. Our experimental average time was 1.41 seconds, and the computational average time was 1.45 seconds. Here are the important laws from physics that we need for this whole experiment. The first is the magnetic field created by the bar magnet, which is found with the dipole moment, the magnetic dipole, and just the field for that. This is from a previous lab. Then we have the magnetic flux formula, which is equal to the area times the magnetic field, and then times the cosine of the angle between them. Faraday's law, which gives us that the induced EMF is equal to negative delta flux over delta t, or the derivative of flux. We have the magnetic force, FB, which equals, this is mu cross B, but which simplifies to 2 pi r, that is our mu. The magnitude of mu, times the magnitude of B from here, times sine of the angle theta between them, and our gravitational force, which is mg. And the important formula for this lab specifically is the time derivative of flux, specifically for this magnetic field, which is from the pre-lecture video number 43. We can see it looks like this. It's 3/2 mu naught, the mu dipole moment, times y, which is position, times speed, times the radius of the ring squared over radius of the ring squared plus position squared to the 5/2. So some system, surroundings, and initial conditions. The system is the aluminum tube and the bar magnet. The surroundings are the rest of the room. And the initial conditions is that the bar magnet is dropped from the rest from above the tube and has a mu or dipole moment of 4.85. Dipole moment, yeah. Experimental setup. So the procedure is just dropping it through the tube 5 times, and each trial is recorded. We then analyze the recordings to find the time taken for the magnet to fall through the tube. Some quick data over here. This is hiding this, but the average time is 1.41 seconds. You can see length, width, radius, dipole again, dipole moment, mass. And here we have our trials and the time that we measured in the videos and our average. The computational model, here are just some code. This is the code for finding the magnetic field, which we saw was this one. Then we have this for finding d flux, which is this whole thing. This is the derivative of flux over time. And this is how we went about finding the forces and getting them to equal each other, not equal each other, finding the net force and then finding the change in velocity and position. Some results, you could see this is a graph of velocity versus time for our magnet, and the computational model gave us an average time of 1.45 seconds. Some assumptions and differences. Assumptions we made was that the external magnetic fields from other objects weren't interacting with the experiment and there was no air resistance. And some comparisons between this and our experiment and the computational model is that in the computational model, the external fields are 0 explicitly. We can be sure that the magnetic field is properly measured and the distance is properly measured. And in both models, we know that there's a magnetic force that opposes the gravitational force and slows the magnet down. Some sources of error, bad timing. We might not have measured the time correctly by using our videos. External magnetic fields, we talked about this. These could influence the fields and create phantom effects. And human error, we might have changed the height that we dropped it at or dropped it in a different orientation. Interpreting the simulation. So for this question, red is counterclockwise and blue is clockwise, and we can tell this using Lenz's law. We know that the induced current has to oppose the change in flux, so it has to be counterclockwise first to oppose the changing flux going down. What happens to the dynamics if you flip the magnet around? No change, but the direction of the current would flip because the flux is now going up. So it'd be clockwise first, then counterclockwise. The computational model is very close to the experiment, but it can be improved by reducing dt, making it faster, and reducing dy, which is making more rings. Or we could also recalculate mu. And the forces are at first unbalanced, but once it plateaus, we know that they're balanced. The acceleration is 0, and that's what's slowing down the magnet. What if question number 1? What if the resistivity was reduced as close as possible to 0? That would mean the resistance of the ring would be very, very low, and by Ohm's law, the associated current would be very, very high. And this leads to a much stronger magnetic field, which might even counteract the force of gravity. Question 2. What if holes or slots were cut into the tube, and how would this affect the ring or currents in your model? If holes or slots were cut into the tube, then the induced current would be reduced because of these holes, and therefore the magnetic field that they're producing would be less, so therefore the magnetic force is less, and it wouldn't oppose gravity as well, and it would fall much quicker. Thank you.